The simplest kind of organic molecules are hydrocarbons. That is, they're made of nothing but hydrogen and carbon. And the simplest kind of hydrocarbons are those that are linear chains of carbon with only single bonds joining the atoms together. We can work out the most basic hydrocarbons just by playing around with carbon and hydrogen atoms. You start with one carbon, satisfying its 4 bonds with hydrogen atoms, and that gives you methane. Then you could take 2 carbon atoms. To fill in the hydrogens, need 6 of those. This is called ethane. Add another carbon, and you have C3H8, which is propane. You can see that we can build up a whole series just by adding more and more carbon atoms to the chain. So let's look at this series in more detail. Hydrocarbons that have nothing but single bonds are collectively known as alkanes. This table shows you the first 10 alkanes, with 1 carbon being added to each successive molecule. Now, there are a few things to note here. Firstly, the word root of each name is important. It indicates how many carbons there are in the chain, and we're going to use these roots repeatedly as we learn to name more complex molecules, so you should memorize them. For instance, if you have a molecule that involves a chain of 6 carbons, then hex is going to be in the name somewhere. Second, note that all the names end in ane. This suffix ane indicates that these molecules are alkanes, in other words, that they have only single bonds in them. Third, I've put in the skeletal or stick structure for each molecule. Note that you can't draw a stick structure for methane, since in stick structures you only show the carbon-carbon bonds. It would also be unusual to use a stick structure for ethane, since it might be mistaken for a dash. Fourth, look carefully at the molecular formula for each of these compounds. Can you see a pattern? Pause the video and see if you can work out an algebraic way to write it down. For instance, if you have an alkane with N carbons, what would its molecular formula be? Well, the pattern is that for N carbons, an alkane molecule must have 2N plus 2 hydrogens. This is because there are 2 hydrogens on every carbon, but the 2 end carbons have an extra one each. So that's alkanes. But what about if we have a double bond in the molecule? When there's a carbon-carbon double bond in the molecule, this changes both the name and the formula of the compound. We indicate the presence of a double bond by using the suffix -ene in the name. So instead of being alkanes, this group of hydrocarbons is called the alkenes. But note that for each individual molecule, the first part of the name, meth, eth, prop, etc., still indicates how many carbons there are. But a hydrocarbon with 2 carbons joined by a double bond is now ethene rather than ethane, which had only a single bond. Here's a question for you. Can you justify to yourself why there is no methane? Now have a look at the molecular formula for alkenes. As with alkanes, they follow a pattern. Can you see it? What would be the formula for an alkene with N carbons? Well, this one's pretty easy. If there is 1 double bond in the molecule, 2 hydrogens must have been removed. So an alkene has 2 fewer hydrogens than an alkane, meaning that alkenes have the formula CnH2n. So we've looked at the alkanes and the alkenes. Finally, for this video, we'll look at the alkynes. If the hydrocarbon molecule has a triple bond, it's known as an alkyne. Again, it's the suffix in the name, the end part, that tells you what kind of molecule you're dealing with, while the prefix tells you how many carbons there are. Can you see what the formula would be for an alkyne with N carbons?